So I hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In my channel, I deal with different subjects ranging from mathematics, physics, chemistry, and biology, and some of the application areas. Kindly check our description boxes for various videos that we have done. And of course, there I'm going to put a link of similar videos, which are, of course, discussions on the same topic. And kindly subscribe to our channel and ring that notification bell for various updates on similar content. So today we're going to look at the concept of the ideal gas equation. And of course, this is going to be a culmination of various laws that we have studied, especially on various, of course, variables of temperature, pressure, and volume. And of course, these general relationships that we have developed for the various, of course, variables that I've mentioned are going to culminate into the concept of the ideal gas equation. Now, this particular gas equation is going to give us general characteristics of various gases. As we had mentioned earlier from our previous discussions, we have said that gases, we're going to treat gases as an homogeneous block, of course, whenever we're going to consider their characteristic. But we're going to also see that there are various ways in which we can describe some aspects of like molar masses and other aspects using the different formulae that we're going to develop from these particular relationships. So in today's discussion, we're going to explore the concept of basically the three laws for the Boyle's law, Charles law, and the Avogadro's law. And this is going to give us a general relationship for description of the ideal gas law, which is our topic of discussion for today. So from the previous discussion, we see that Boyle's law gives the relationship between volume and pressure. And of course, I can just give that one in terms of algebraic representation, whereby we said that the relationship between volume and pressure gives us an inverse relationship, which basically can be given in terms of V is given as K over P, given as such. So therefore, this is the implication of Boyle's law from the relationship between pressure and volume, which have an inverse relationship, and therefore that's going to give us a break representation of the law given in that specific format. And then we're going to look at the Charles law, whereby we see that from the relationship between volume and temperature, we say that volume is directly proportional to temperature. And this, of course, is going to culminate to Charles law, whereby we say that volume basically can be given as a product of a constant times the temperature given as such. And that is going to be giving us the algebraic representation of Charles law. And then lastly, we said that Avogadro gave the relationship between the reacting volumes of gases, whereby Avogadro had, of course, given the relationship between volume and the number of particles which are going to be involved in a reaction under the concept of constant temperature and pressure, whereby said that the volume that is involved is directly proportional to the number of molecules. Thereby, we developed the relationship of Avogadro's law of volume is equivalent to n times k given as such. So the combination of this Boyle's law, Charles law, and Avogadro's law, of course, it can be given in terms of a relationship, whereby we are going to see that all the three laws are going to give a description for volume, and therefore that's going to give a general relationship for finding the ideal gas equation given as such. So basically, we can give a general description and therefore volume, whereby we have said that the volume is directly proportional, or can be given a proportionality using this Boyle's law, whereby volume is proportional to the inverse of the pressure given as such. And then we're going to see that this specific volume, according to Charles' law, is directly proportional to temperature. And then lastly, we have said that the volume is directly proportional to the number of molecules given as such. And of course, the data on these particles, we're going to see that these are going to be basically the concept of the number of moles, as we're going to be describing them later in the ideal gas equation. So therefore, we can have a general description for this particular volume by having 1 over P times T times N given as such. And this is going to give us the general description for volume, whereby V is equivalent to Tn over P. So basically, this implies that the product of pressure and volume gives us Tn, and of course, this is going to be a constant which is involved in this specific relationship. Now, this constant is basically what we refer to as a gas constant, which we are going to give in terms of R. So therefore, we can have this a specific representation of a PV given in terms of a nRT, whereby P implies pressure, V implies volume, N is the number of particles as we said, and then we're going to have R as a gas constant, and this is absolute temperature given as T. Now this basically entails what we call the ideal gas equation, which is going to give the relationship between pressure, volume, and temperature of specific gases that we're going to consider for ideal gases and or rather mixture of gases, as we have said. Now in this case we're going to see that from the experimental values, this particular ideal gas is going to be basically non-existent, but it's going to create a basis for us in trying to describe some characteristics of various gases. Now I've mentioned the concept of this particular ideal gas being non-realistic, in a sense that basically naturally we're going to see that from experimental values there are going to be some slight deviations from this particular relationship that we're going to see being given by the ideal gas equation. And of course later on we're going to see that we can develop another version of this ideal gas equation that can describe the actual or the real relationship that exists between either pure gases or a mixture of gases, as we're going to see later. Now, of course, this is going to be, this particular version of the equation is going to be given in terms of an equation of a state. And of course, that is going to be expressed in terms of the van der Waals equation, which I'm going to discuss in our next relationship. So basically, I presume that we have understood how we can come up with a general relationship from the three laws of the Boyle's law, Charles' law, and Avogadro's law, which are going to culminate into an ideal gas equation. Now, in terms of application, we're going to see that there is going to be a different behavior that are going to be displayed by these particular gases for the real gases, basically, which are going to be a deviation from the ideal gas relationship that I've given above. And this can be explained in terms of course, this particular relationship of pressure, temperature, and volume, using an equation of our state, which I've said we're going to discuss in our next discussion. So that is it for now, guys. Kindly subscribe and engage us in the comment section for more, and also ring that notification bell to be getting updates on various uploads that we do on topics of mathematics and sciences. So that is it for now, guys. Bye. God bless you. Catch us in our next video.